ECE 111, UCSD, Lecture 4 and 5, Combinational Logic and System Verilog. First, we will be talking about System Verilog modeling levels of abstraction. There are different levels of abstraction we could define for our programs, and typically what happens is that, the highest level of abstraction is a behavioral level, but behavioral level may not have all the accurate details of a design. As we go down the level of abstraction, we may be talking about how the data flows in this behavior. We will be talking about data flow modeling in this lecture, and then, finally, we could do gate level modeling like you would do for a Boolean logic, but it would not be as easy programming as it is to program in a higher level. And last but not least, even the switch level implementation is available in Verilog. So let's go through the details. Typically what happens is that the RTL model, which is the model we are going to emphasize in this course, is using a combination of behavioral and data flow style. So we will be mostly focusing on these two in this lecture, even though we will be mentioning the gate level and switch level as well. So the behavioral level modeling, the design is just telling you the expected behavior, but not about, we don't worry about implementation details. For example, if you want to do, say, multiplication or addition, you just say A is equal B plus C, and then that is enough at the behavioral level to say what is the behavior of this designs. These are also algorithmic models, robust functional models, and this is the highest level of abstraction we have. We could use this to describe complex circuits, and we typically just use it because it's complex circuits, and we've already discussed complex circuits have to be sequential. This is what we use here. We make the sequential logic using this, and this is the closest to the natural language description of the circuit functionality. And then behavioral models are usually faster to simulate because it's a higher level model, doesn't go into all the details. We could use Boolean logic, truth table, or algorithm to describe the behavior. The behavioral modeling is typically done using two important constructs, the initial and always construct, and they usually appear within these two constructs. They are executed concurrently, model parallelism is assumed, and then it may not be necessarily synthesizable. Let's take a look closer. What is the difference between the behavioral level modeling and RTL, which we described earlier? So the behavioral level description of a 2-to-1 select multiplexer, we've seen how we described it using the if-then-else statement before. Here we had a input that is in logic, just taking 0 or 1, and then we used the sensitivity list with always, which is active if the select signal is available, and then simply if select is 0, the output is going to be the first input, and if the select is 1, the output is going to be the second input. This is using if-then-else statement, and it's just going to synthesize into what you see on the left. And now if we use the same, do the same circuit using the case statement, we could just say, based on the select signal, we are going to select, assign the output to the input, and then AND case and AND module is going to be used for this case. And the synthesis is going to be the same. So in data flow modeling, the module is explained by just describing how the data flows. And typically we've seen this before. It was like, the Boolean logic we've used before that has been used for this, and this is higher than the gate level. And In data flow, we use a continuous statement to derive a value into an output net, and we've seen this before for combinational logic. If you remember from before, this is going to be evaluated whenever the operand changes, and the left-hand side must be a scalar or vector. It cannot be a register, while the right-hand side could be anything, and the delays can be specified. So this is something that as we discussed, is not synthesizable to hardware, but it's useful if you're doing simulation in this setting. Now assume that we want to describe the same multiplexer we've seen before in terms of how the behavior of the logic looks like. We've seen the logic description before. This is going to be how it looks like based on the select signal and first input and first output, and it's going to be translated post-synthesis into these gates that are a little bit lower description than the behavioral modeling. Last but not least, the RTL modeling is a combination of the behavioral and data flow modeling, but here they don't really contain the details but of how implementation is going to be done in hardware, so it's a higher level abstraction, but they do simulate faster than the gate level and switch level, which we will be discussing. And the RTL modeling has two primary constructs. Let's go to the board and see how they look like. So here I'm writing the behavioral versus RTL side by side, so you see how this looks like. What is the behavioral is a high-level description, just like, if you want to write a sum, it's A plus B is equal C. However, if I want to write register transfer level, what happens is I need to define like registers, and I have to define how the carry is done and how the clock is connected. In this particular case of the RTL, this should be synthesizable to hardware. So this is synthesizable. But this here, what synthesizable means that when I'm using the language constructs, I should be just using the synthesizable one. So, but here, if I'm talking about the behavioral model, where I'm just describing, A plus B is equal C, what happens is that I can make things that only work in simulation and not for synthesis. So all language constructs that are used in simulation and synthesis can be used here. And so this is not necessarily synthesizable to hardware. And here I also need to know how the clock is connected, and only I'm going to be discussing the logic that is happening between the clocks. So this is basically a combinational logic that happens between the flip-flops, whereas this one is going to be arbitrary. So this is taking place, in almost, single clock cycle, and this one can take arbitrary number of cycles to be implemented. I can define a notion of a time here, and here, because it's only synthesis, I cannot have defined a notion of a time. Now, in terms of the language construct in RTL, I'm going to be using mostly always and assign. And this is, we have seen these before, how we could make the combinational logic using the language or assign. So combinational logic can be done using the always and assign statements. Mostly here, what we do to use the behavioral model, which is basically a finite state machine or a sequential design, we typically use the initial and always to describe the language. So this is just a summary of how the behavioral versus RTL looks like. They both are used. This is kind of more algorithmic level for the designer. This is more for the hardware synthesis perspective, and they're both very useful in a typical design.